Thanks. It's a pleasure to be here at CCCG. Um, though this is the Paul Erdős Memorial Lecture, I wanted to um, tribute, do a tribute to Godfried Toussaint, this guy who died just before last CCCG, um, and seemed like a fitting time to talk about him and his work, and in particular, uh, what I learned from him and a lot of the uh, fun research that we got to do together. Um, and this is me with a much longer beard. And this is my dad, who's also watching. Um, so let me tell you a little bit about Godfried if you didn't get to meet him or didn't know much about him. He was born in Belgium. He grew up in South America. He went to school in the US and in Canada. And then for a long time, he was a professor at McGill. From 72 to 2007, he became emeritus, won a lot of awards. Notably, he founded this conference in 1989, when it was held in Montreal. And he also founded Sausage, the other computational geometry conference. He lived around here at Harvard 2009, 2010. We got to hang out a lot then, and became a MIT affiliate when he started working as the head of computer science at New York University in Abu Dhabi, 2011. This is his daughter, several years ago, Stephanie, and his wife, Eva. But to us, he's the father of computational geometry. Most researchers in North America can trace their interest in computational geometry back to Godfried through others. Beyond geometry, he connected to a lot of other fields, computational geometry plus X for many values of X. I'll show you a few of them here, most famously music, but there are a lot along the way. In general, he was very collaborative, and he read a lot, especially in other fields, which let him combine these things together and had lots of cool ideas for how to do it. Generated lots of great open problems, and he was super warm and caring and open. So we met through this series of workshops in Barbados. McGill has a Bel Air's Research Institute in Holetown, Barbados. He's been running workshops there for 35 years, long time. First one I went to was in 1998. Back then we didn't have digital cameras, so the first photos I can find are from here in 2000. And every year we met to work on problems. Godfried organized these workshops. Towards the end, I co-organized with him. You can see a lot of luminaries in our field, like Dror O'Rourke here, Vida Dujmovic, Jit Bose, Dave Rappaport, Ferran Hurtado. This year, 2009, I think is when we had both a geometry workshop and a music workshop in parallel. This is one of the music sessions. This is when Stephanie was an assistant organizer. And this was the last year that this workshop was held, because this year was canceled because of COVID. And also the last year that Godfried attended. So these Barbados workshops, I first went there when I was 18 as a PhD student, and it was really formative for me and for a lot of people who attended, and I think by extension others, and how collaboration should be. This providing a collaborative environment and experience for people, I think, is what has made computational geometry such a collaborative field. It's rare to see a sole-authored paper, and almost never do you see a paper that's not alphabetical order. And Godfried would tell you, and Erdős would tell you, and I would tell you that collaboration is a great thing to do. So especially for the students in the audience, I encourage you to always collaborate, never work alone. You'll be more productive because you can combine the tools of multiple people together, and it's just a lot more fun to do research in a collaborative way because you also get to hang out and be social with your friends while you're also doing hard research. So Barbados is one way to do this, but it's not the only way. And so while I used to call this model of collaboration the Barbados model, that's a little bit exclusive to those who get to go to the Barbados workshops. In principle, anyone can organize a workshop, though it's pretty hard right now. And so we've introduced, just in the last couple of years, a new term for this model, which we call super collaboration, to make it sound cooler. And there's a website for it you can check out, where we're trying to encapsulate Godfried's approach to collaboration, this idea of groups brainstorming to solve problems where we just care about truth and solving the problems. We provide a positive and encouraging atmosphere to, anyone can suggest their ideas. There are no bad ideas. And the authorship model is very liberal. So the idea is that everyone decides for themselves whether they contributed enough to be an author. So you're never worried about whether your contribution will be considered significant by others, because you get to judge that. And authorship is always alphabetical. The Barbados week-long workshop, where you super intensely work for a whole week, is one way to do this. But another effective way is the weekly meeting style over a longer period of time, years or semester. You can work on problems just once a week for a couple of hours. So I do this in my research group, and many of you probably do this in your research group as well. So you may not know it, but you're already doing super collaboration. It's just a term for it now. But a recent direction that I've been enjoying a lot is integrating super collaboration into my classes, in my graduate classes, where students learn the state of the art of the field, and then at the same time, they can try to push that state of the art forward. I think that's a really powerful way to get students excited about research. Also undergraduate students, but especially graduate students. So I'm going to show you this in a little bit more detail. I'll just mention there's a document if you're interested in embracing super collaboration more. Even if you're already doing this kind of collaboration, I'd encourage you to read this over and let us know if you have any feedback or ideas for trying to document best practices. Try to encapsulate what Godfried did so well in bringing these groups together. We've also been building software to make super collaboration easier to do. Especially easier to write notes down, because it's really important to keep notes of what you do, otherwise you'll forget. And so this is a free open source system called CoAuthor. It's on GitHub, and it's a threaded discussion forum where you can easily write LaTeX, post images, and multiple people can write notes. You can edit it in parallel. And you can reorganize and do all sorts of things. So the idea is that everyone can write and read and organize their text and math and images collaboratively in real time. You can write little short messages. You don't have to write a whole paper, because maybe you don't know whether this is going to be a paper yet. These days we're using it to actually collaborate, but the original goal was we're collaborating in person, and we just want to remember what it is that we did. When it comes time to write a paper about our results, then we have lots of notes that keep track of that. By now, there's over 1,000 people using this system across the world, over a dozen different research groups, a growing number of research workshops. I've used it in a lot of my classes and a few other MIT classes. And this summer, it's being used by high school and undergraduate research summer programs. Especially with COVID, it's a useful augmentation to the standard meeting. If you're interested in using CoAuthor, let me know. But I wanted to tell you about how I use it in the classroom and how super collaboration fits into the classroom, where this was a novel idea at the time. Now probably a lot of classes are going to be organized this way, that instead of using in-person meeting time for delivering lecture material, all of the lecture material is pre-recorded, and students watch that in between the synchronous meeting times. And then when we meet, students can ask questions, though this is a little less exciting. The exciting thing is to solve problems together. And in an undergraduate setting, this idea of flipped classes is not new, and typically you present problem set style questions to get students to engage with the material. But in a graduate setting, you can use the same idea to explore open problems and get students to explore, do research in class. I think it's a really powerful way to do it. This is a little video of was recorded the last class I did in this form, which was a year and a half ago. So students are working on whiteboards, meeting around tables in this nice sort of open space, and then they're posting all of their ideas and notes from the in-person meeting onto CoAuthor, which I then review at the beginning of each class, give a kind of progress report, which problems have been solved or what progress has been made. Students can work on open problems or they can work on solved problems. It's up to them. But most of them engage at least a little bit on open problems because it's exciting, and we solve a lot, actually. And so encourage you to try this in your classes, especially with things online. If you're recording your videos ahead of time, it's pretty easy to try. So I first did this in my folding class, Geometric Folding Algorithms 6849. The requirement was that every student should post at least once per week, but students really engaged with the problems, and the average number of posts per week was 4 per student, which is pretty cool. We worked on almost 200 problems, some solved, some open, some design questions for the more art-oriented students, and we produced, I think, about 8 publishable papers, though they haven't all been written yet. The most recent experiment was in this Hardness Proof class, which is where that video came from. All of these classes are online. If you want to watch the video part, like the technical content, you can go see them on my webpage. But the research part is not public because we're still writing all the papers that came out of it. This reached a new high of 5 posts per student per week. And I estimate about 30 publishable papers. We've written over a dozen out of this class so far, and still a lot to come. So this can be a really productive way to do research. If you're in a field with lots of open problems, it's, I think, a powerful way to get your students to work together. Certainly harder online. This year in March, we couldn't go to Barbados as originally planned. So we tried a first experiment at a virtual workshop in computational geometry instead of a Bel Air's workshop on computational geometry. This is the group photo from that meeting. Some of you are probably here. And it was fun, definitely not as fun or as productive as a typical Barbados meeting, partly because we're still figuring out, especially back in March, the best way to have these kinds of meetings online. It's harder for sure, and we've been trying to build more tools like CoAuthor to make this more tractable. So a new system that I've just been working on the last couple months is called Co-Create. This is a shared whiteboard tool because we found frustrating the existing whiteboard tools where everyone can draw on this board. You just instantly create a room, share a link, and then anyone can go and edit that. In fact, by sharing this link now, maybe people will go and change this board. But this was a n over 3 guards proof idea. You can see everyone's cursor. It's pretty simple but effective, and it's again open source and free. So let's. That's the sort of super collaboration story. I encourage you to try it out, especially if you haven't already. I'm now going to talk about research that I did with Godfried, some of my favorite things of his and mine. And it's going to loosely tie together these 5 great mathematicians. We've got Euclid, Euler, Gauss, Erdős. This is the Erdős Memorial Lecture, after all, and Godfried. I only met Godfried among these 5 people, sadly. But they will all play a role at some point in this talk. So one of our first papers together, this came out of the Barbados workshop in 1998 where we met, was about locked and unlocked polygonal chains in 3D. You can see there's lots of authors here, so this was a Barbados paper. And it's about these chain linkages where you have these rigid bars connected at hinges which can rotate to any angle in 3D. And the result that we independently discovered and then realized Cantarella and Johnston proved this in just the year before, is that there are some chains that are kind of locked. They can't be straightened out without collisions. I won't go through the proof of this, but it's fairly simple. So this raises the question, which chains can be straightened? And one result from this early paper is that if you have a chain and there's some direction you can project it onto a plane where there's no crossings in that projection, then you can always straighten it. And it's kind of a fun proof to look at. So the idea is to try to accumulate into a near vertical chunk one segment of your chain, and then if you have if the next link is not vertical, you can just rotate it up to be vertical. So that's sort of the easy case. And if you're careful, you stay within your original projection, so you will avoid crossings. If your angles are more like this, though, then you end up accumulating not a straight chain, but a monotone chain. And so in general, this is going to be some wiggly thing. And so you have this monotone chain with a single move. You can make this edge almost vertical, and then you rotate this around to align with your next edge and repeat. So fairly simple, but cool. It's still one of the main positive cases we know for 3D. Another positive case is if your chain lives on the surface of a convex polyhedron, then you can also straighten it. Here I've drawn a very simple polyhedron, which is just a square, but it also works for multiple faces. The idea is you pull your chain up into a vertical thing, and you can just grab the next link by rotating it like so. Then you switch which plane you're looking at, because this plane would be the next one, and then you rotate that up. So cool. And then we spent a lot of time back in 98, 99 generalizing this from chains to polygons, where the graph is a cycle instead of a path. So if you start in the plane, then we showed you can lift the polygon up into a convex arch. We call this the St. Louis arch algorithm. And we spent a lot of time seeing how can you sort of add one more triangle to your convex polygon one at a time. Which led us to a problem of Erdős, actually. We independently discovered it and then realized, Erdős worked on this in 1936. And I even talked about this in my first Erdős Memorial lecture back at CCCG 2006. This is what my slides looked like at the time. Apologies for the Comic Sans. What was this Erdős problem? Sorry, 1934. Correct myself. Take a polygon and take its convex hull, blue, and then this decomposes the polygon into the interior, this purple stuff, and these pockets, the blue pockets. So we're going to take one of these pockets and flip it out, and then pick another pocket, this one, and flip it out, and so on. And then, in general, keep taking the convex hull. This always defines some pockets, unless you're already convex. Flip them out. Keep finding pockets. Keep flip one, flip one, flip one. Keep going. I think there's one more here, which I didn't draw. After you do this last flip, your polygon will be convex, and then you stop. So the problem that Erdős posed in American Mathematical Monthly, this is his entire article, is proved that this will stop after finitely many steps. And this is relevant to 3D linkage folding because you can view flipping a pocket as this kind of continuous rotation through 3D, where you take the lid of the pocket here as your hinge and you just rotate about that hinge. So you can execute these flips in 3D. So that's why we got interested in this. This would be one way to do it. One way to convexify any planar polygon using 3D moves. But it's not obvious that it converges in finite time. So a few years later, Naj in the monthly wrote this article, it's like a page and a half, proving that it works. First, observing that a slight detail in Erdős's posing wasn't right. Erdős said, let's flip all the pockets at once. But if you do that, you can get collisions. So that's not so nice. So then he looked at the version where you just do a single flip at a time, and he proved that that always works. So great, problem solved. But this was the 30s, and there were many other researchers that, because it's a natural problem, just came up with this problem and then also solved it. Some posed it, some solved it. I think most of these were, this is, I think, a group, although these guys, this one knew about Naj, and then this was a completely independent discovery. And Grunbaum was the first to realize all this literature was connected. And then Godfried wrote a nice survey paper about these different proofs, and he gave his own proof for this theorem. So that's the Erdős-Naj theorem. And so I cover this in my geometric folding algorithms class. So I thought, okay, great. I will cover the latest and greatest proof by Godfried, 2005. And so let me give you a rough idea. Imagine that we had some infinite sequence of polygons from this flipping process. So we start with P0, then we produce P1, then P2, then P3, each with a flip. And if it's infinite, we want to get a contradiction. So there are three main steps. First, we're going to argue that the sequence of polygons has a limit, so some polygon P star that we're approaching. Then we want to argue that that limit is convex. This is easy. Godfried says if it's not convex, then we weren't finished with the flipping process. So we could do another flip. So if we're taking the limit of all the flips, that should be convex. And then the third step is that once a polygon gets close to the limit, you're actually done. Okay, so I presented this proof to my class, obviously in more detail, and a student raised their hand and like, I'm not sure I buy that step too. And maybe you saw the issue, but I'm trying to present these proofs as if they sound correct, but it's actually not correct. Because of this issue that, let me clear this image. Suppose you have a polygon with two really complicated pockets here, and maybe you spend all your time convexifying one, and your limit is just spent with the infinite number of steps it takes to convexify that one pocket, and you didn't touch the other pocket. So you may not have fully finished the flipping process, because the whole issue is, what if it's infinite? So that proof doesn't quite work, and so I wrote to Godfried. It's like, this seems to be a problem. So we started looking at the other proofs, figured, oh, well, maybe the oldest one is the nicest, because it's very short, and it's easier to get than translating the Russian proofs. And it differs in exactly this step of arguing that the limit is convex. And so their proof is quite nice. It says, okay, each polygon is contained in the next polygon, just because flipping expands the polygons. Let's take the convex hulls of those polygons, CK. Well, the convex hulls are also nicely nested, because, again, each pocket flip expands the convex hull. And then each polygon is contained in its convex hull. And so you get this nested sequence of polygons and their hulls, and the convex hulls converge to a convex polygon because they're all convex, and so therefore the polygons converge to a convex polygon, namely that C star. Right? Maybe? No? This also is incorrect because, again, of multiple pockets. So, I mean, Erdős made this mistake, but Naj made this mistake also. When you have multiple pockets, you only flip one of them at a time. The convex hull of P0 here is this square, but if I flip just the left pocket, there's no containment relation between this square and this shape. Okay, so that doesn't work either. This containment is correct. And just to, again, especially for the younger people in the audience, never use the word obviously in your proof. That's exactly the sentence of this proof that is wrong. It may be that one of the papers, being in Kazarinov, actually realized this. They have this one sentence, which I've included the Russian here, very short, saying this proof by Naj is wrong, but it doesn't say why. And Grunbaum read this, but there's no basis for the claim, so it's hard to verify. So anyway, talking to Godfried, I said, hey, maybe we should write a paper where we give a counterexample to your own paper. This is a reference to a series of papers that Godfried wrote, which are counterexamples, and he vowed to never write another one. But he said, I'll make an exception this time, since I've never written a counterexample to my own paper. And the other people are all dead, so it's reasonable to give counterexamples to them. And so I had never actually looked at these papers, so for this talk I did a little survey. These are all of the papers he wrote in the 70s that are counterexamples of some form. They're all called comments on such and such. His first one is very cautious. He says, we think the interpretation of the optimality and the assumptions need more clarification. But he very quickly gets to a counterexample is given. Actually, this is a response to a counterexample paper giving an even stronger counterexample. So that one is positive. But a lot of these are like, okay, meaningless experiment. This one, there's a response from the author. They were not so happy. They're incorrect labeling, counterexample to this claim. This you're comparing to the wrong thing. Sometimes the authors thank Godfried for their input, but sadly, not everyone took this well. And these are he only wrote a few counterexamples in the 80s and 90s papers. I talked to Godfried about this, and he said, he assumed that everyone just wanted to know the truth. We're all seeking mathematical truth, and we want to know what is true and what's not. And so he assumed that people would take these as they were intended, but unfortunately, people took them as more personal attacks, and so he stopped writing these counterexample papers and instead talking directly to the authors, because he still read a lot and still found a lot of counterexamples. A lot of these counterexample papers actually led to better algorithms later, but he didn't want to make enemies. He's all about friendship. So his last counterexample paper is looking at all of these so-called proofs of the so-called Erdős theorem. And we found that most of them, we translated all the Russian ones, most of them are flawed. There are a couple that are mostly correct, but a little bit terse, or imprecise. And so we wrote our own proof that aims to be fully complete. It's fairly short proof, and hopefully correct. I'll give you a little idea of how this works, just a visual overview, because it's kind of a fun argument. The idea is to start with some point x interior to the polygon and then look at some vertex. Every time it flips, its distance to x increases. And so this means these distances increase monotonically, and so they converge to a limit. Then you do that for 3 different points, x1 through x3, and you get that any vertex converges to the intersection of these 3 circles. And so every vertex converges to a point. So that's good. Then furthermore, every time you flip a vertex, it switches between here being reflex and being convex. So its angle changes by 180. And so if a vertex is going to flip infinitely often, then its limit angle must be 180 because it's converging to a point, its neighbors are converging to points, so the angle converges. So the only thing it could converge to and flip around 180 repeatedly is 180 itself, which means that the vertices that are not flat in the limit actually have to stop moving after finitely many steps. And they're the only vertices that contribute to the convex hull, and therefore, once they stop moving, actually everything stops moving because the other vertices must already be flat. So that's a high-level idea. Nice, clean argument for why the limit is good. The same argument generalizes to non-simple polygons as long as you don't have a vertex with a 360-degree angle, a hairpin, or 0-degree angle. It's open without that assumption. The big open problem, though, in this field, which goes back to 1998 when we started working on it, still open, is can you bound the number of flips into reasonable parameters like the number of vertices and the feature ratio? We know that number of vertices alone is not enough. Even with a quadrilateral, you can have arbitrarily many flips. But presumably, these 2 parameters together, you can get a polynomial bound, pseudo-polynomial bound, but don't know. In the spirit of super collaboration, I'm going to try to highlight open problems in all the stuff that I talk about. So this was not Godfried's first paper about history of mathematics. He wrote a bunch of nice papers. One of my favorites is this new look at Euclid's second proposition. So, Euclid was more of a compositor of the mathematics around him. And some people don't like his proofs, though he was certainly the beginning of one of the beginnings of formal argument. This is, 400 BC or so. And the trouble is that his big magnum opus, Elements, was destroyed in the fire of Alexandria. We don't have the original book, so we don't know exactly what he wrote. But we have various copies and translations that were written by others. And there was this one bug in Book 1, Proposition 2, which is about ruler and compass models of computation, that a lot of people thought Euclid got it wrong. And Godfried read all of the different translations, maybe not all, but many of the different translations of Euclid, and found that actually there's one translator that probably introduced this bug. It wasn't in the Euclid's original because there are other translations from the original that did not have this bug, and instead all of the children of that particular translation had the bug. So pretty cool historical analysis, restoring honor to Euclid. So now I'm going to transition into computational geometry plus X. One problem that we looked at a Barbados workshop, I think around 2004, 2005, was this is instance-based learning. Before deep learning was cool, Godfried was looking at it. And so this is a problem where you're trying to learn some rule for characterizing data as living according to, say, two different types. Maybe it is a cat or it isn't a cat, for example. So maybe purple it's a cat, and these green or yellow dots correspond to not a cat. And you want to try to figure out what is this boundary between cat versus non-cat. This is sort of one of the general learning problems, well studied. And we were looking at this nearest neighbor rule, which naturally begets a Voronoi diagram. So you want to compute this Voronoi diagram efficiently. And what you really care about is this boundary. You don't care about the whole Voronoi diagram. You don't care about all of this complexity in here. And so what we showed in this paper is that you can improve n log n running time to n log k, where k is the number of sites that are actually involved in the boundary. And this also works for more than just two colors. And so I think this is a pretty cool start to efficient instance-based learning, nearest neighbor rule. In practice, people use J nearest neighbors, so like a jth order Voronoi diagram, so that we didn't look at. And of course, they're in more than 2 dimensions. But I think this is a pretty cool application of computational geometry. I know Jeff is here in the audience. So the next computational geometry plus X happened to me when Godfried visited in 2005. Just as a fun break, we also went to this big party, infamous party at MIT called Steer Roast, which features mud wrestling, among other things, giant fires. And he also visited the MIT Glass Lab, and he made this glass sculpture, which is pretty cool. And I love this phrase that he used in his email: "The convex hull of my life has several new vertices." I think that's a great way to think about life, speaking as a computational geometer. And so we ended up working on this problem called sand drawing or Sona drawing, and there was a CCCG 2006 paper about that. This is what the title slide looked like at the time. This is a talk given by Erdős Toussaint. And so what is sand drawing exists in many cultures. We originally learned about the Sona practice by the Chokwe and Lukazi people in Central Africa, where it's used as sort of a storytelling and maybe religious practice device. This is a modern take on Sona drawing, which I found on Instagram. It's pretty cool. Cultures using it to make art, in this case, limited edition screen prints. You can still buy them now. But in general, they often start with little points and draw curves around those points. And then there's related practices, Pulikulam in India, and the Nidus practice in Vanuatu, which is a country in South Pacific. But we're going to formalize this into a mathematical model to try to get some interesting geometric questions. So for us, we have a set of point sites. And then we want to draw a single closed curve that only has proper crossings, just two-way crossings, never tangencies, never just touching. And there's exactly one face for every dot. That dot is in that face, excluding the outside face. Okay, so one bounded region per site. Nice model. You can try to characterize these. I wanted to connect to Gauss. So these are related to a notion called Gaussian graphs, which is a stronger version than Eulerian graphs, where not only is there an Eulerian cycle, but there's a cycle where you go straight at every vertex. So here, for example, if I go straight, I end up making 2 cycles, not 1. And so this graph is not Gaussian, but this graph is. And we're interested in Gaussian graphs where we only have these 2-way intersections, so degree 4 Gaussian graph. So the problem we looked at is if I give you a bunch of point sites, construct a SONA drawing. But I may have various constraints on it. For example, I might have 2-colored the points, and I would like every Gaussian graph is face 2 colorable, and maybe I want the face 2 coloring to match the coloring of the points. So that's this first condition. Or maybe I want the shortest length SONA tour, or I want the SONA drawing that has the fewest line segments, forbid smooth curves. Or maybe I only want to turn right. Maybe I want to minimize the amount of turning or winding I do. Or maybe I'm restricted to work on a grid. A lot of actual drawings are on a grid. You can see this one almost is. So here's some basic results that we proved back at CCCG 2006. Every point set has a SONA drawing. You just take a TSP tour of all the points except for one of them, and then just loop around each of those points except for that last one, and just make sure that last one is enclosed in sort of the big face of the tour. So it's definitely possible to do these SONA drawings. You can, with the same argument, you can only turn to the right. Just keep looping. But more impressive is that you can do this also with 2 coloring and only turning right. This proof is more involved, but the idea is to squish all the points so they're almost horizontal, and then decompose them into segments that are blue, 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 red, and then segments, this one happens to wrap around, that are red, 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 blue, and alternate between those 2. And then you do this sort of local construction for each of those groups. Okay, so that was 2 coloring, cool. How about minimizing number of links? So this is a nice example of only 8 links to visit 7 points. Again, we're squishing the points to be almost horizontal. Doesn't make much difference. And in general, we can almost characterize the number of links you need for n points, but there are some gaps, like here between n+1 and n+2. So some open problems here if you're interested in exploring. And the proof of this is actually fairly simple. We just took exactly 3 really well-drawn examples, including this one that I showed you, and then just observe that you can glue these together because they have vertical segments on the side. I can remove 2 links and 1 point and combine these, and you can show that all integers can be represented pretty well with these 3 examples. But with a little more even computational work, we might be able to find better bounds. Okay, what about SONA on a grid? This is the last topic. Suppose you have your dots as interior to cells of the grid. There's some point sets, like this quincunx position, that cannot be, there is no SONA drawing, because you are, in this case, you're forced to draw all of these segments. And then if you connect them in the obvious way, you get 2 different cycles. If you try to do any other connection, you'll end up making another face with no point in it. So that's not allowed. So some point sets don't have grid SONA drawings. But if you take any point set and you scale it by a factor of 3, then it's always possible. This is an idea of how that works. But I think this is the most beautiful still open question in SONA drawing, is what if you scale by only a factor of 2? Can any point set be grid SONA drawn? Still don't know. Some positive evidence is we know that if you take a full m by n array of points and you scale by a factor of 2, then it can be drawn. But this construction that we're showing is very specific to that point set. If you omit some of the points, we don't know how to do it. So that was back in 2006. At this CCCG, and in fact the very next session, David Epstein will talk about our new paper, which proves that without scaling, deciding whether a point set can be grid SONA drawn is NP complete. It's a reduction from planar 3-sat. I won't go into the details here, but there's a lot of fun gadgets here to make sure everything connects together into one big cycle. And then the last problem we explored was how do traveling salesman tours and minimum length SONA drawings relate. So we can convert any traveling salesman tour into a SONA drawing, so we have this inequality. But in fact, they're within a constant factor of each other. We proved this back in 2006, where the constant we know is about 1.6. And still open problem is this the best relation you can get between TSP and SONA? And back then we had this example, which proves a separation between the minimum TSP tour, which is this red thing, and the SONA drawing, which is the formerly purple thing, of about 1.05. So a big gap between these two. And the other thing we explored in this year's paper is getting a better example where TSP, or SONA divided by TSP, is now 1.55, which is pretty close to 1.64. But still some gaps to do. It's a cool kind of fractal example. It just keeps going in here. And if you're interested, we also proved that minimum length SONA tour is NP-complete, which is an open problem from Godfried. And if you're interested in more, you can check out David's video presenting these results and the paper. This is a paper dedicated to Godfried, and we worked on it starting at the virtual workshop on computational geometry, the goal of solving some old Godfried open problems. So we succeeded, though there's still lots more to do if you want to join. All right, the last topic I want to talk about is computational geometry plus music. Godfried was really into music, and he grew up in Latin America. I assume he was surrounded by drumming, but according to his own bio, he got really started learning to drum in Canada, and he belonged to this troupe, Yorosu, from 97 to 2001. Did West African music. He did lots of different drumming things. Another fun band he was in was the Algorithmics, Professors of Rock at McGill. For us, the most famously performed at CCCG 2008 banquet with some other friends like Stefan Langerman here. I love in this website, which is still up, he's called Godfried the Terminator Toussaint, because I think he was like a robot, always perfectly on time. So he loved drumming, but he also loved combining his computational geometry with his interest in rhythm. And this culminated in a book in 2013 called The Geometry of Musical Rhythm, What Makes a Good Rhythm Good. He dedicated it to his wife, Eva. This is a little review. Lots of glowing reviews, both in the music and in the mathematics side. It's a fun read. I definitely recommend it. Lots of little chapters, each with little vignettes into mathematics of rhythm. And I wanted to show you a little bit about that. So these are the so-called 6 fundamental African and Latin American rhythms. Chico, Clave Son, Rumba, Sukos, Gahu, and Bossanova. I'll play for you, I will attempt to play for you the Clave Son. This was, I think, Godfried's favorite rhythm. So you can, I think hopefully the notation is clear. We're starting up here. We're going to go clockwise. And whenever there's a black dot, I'm going to clap my hands. And whenever there's a white dot, I'm going to do nothing. And then it's going to cycle. So it should sound like... This was pretty much the call to, whenever we were in Barbados and we wanted to do a progress report, everyone would start clapping that. We'd all come into this synchronization, and then we'd all meet and talk about what we did for the day. So beautiful rhythm has this kind of call and response structure of setting up one rhythm, which is playing every 3 notes, and then sort of responds with playing every 2. There's a whole chapter about it in the book. So we can measure a couple of different things. So we have these points which are called onsets, and we're going to say there's k of these onsets where I'm actually clapping my hands. And then we have the times in between, or all of the times. These are called pulses. So that's just available time slots in the timeline. And we can measure the distance between onsets in 2 different ways. We can measure them sort of clockwise around the circle. How many pulses, how many time units were there between 2 onsets, so this would be 3. Or we could measure, Godfried liked to draw these as actual polygons. So there's this pentagon here, which is representing this Bossanova rhythm, say. And we could measure this distance, which is square root of, I have no idea, something. So we call the first one the interval. This is like time distance. And the second one is distance for Euclidean distance. Okay, and I'm going to use both. So that's why I wanted to mention both. And so the first notion of a good rhythm is a maximally even rhythm. Turns out Bossanova is maximally even because among 5 onsets and 16 pulses, n is 16, k is 5. I didn't mention, but all of these rhythms have that same number of onsets and number of pulses. This one maximizes the sum of pairwise Euclidean distances. Now, this is not an interesting property if k evenly divides n. Then you're just going to be playing a boring rhythm like, okay, pretty boring, always the same interval. And so to make things interesting, we're going to usually assume that k and n have no common divisor. So you don't get any of this boring behavior. You might ask, why do we define evenness with distance instead of interval? This is basically to disambiguate things. Otherwise, all of 6 rhythms I showed you would have the same goodness, same evenness as measured by intervals. But by distances, this is the unique maximizer. In fact, it is always unique. So let's play Bossanova. So this is, let me first play Clave Son in the top center. And then this is Bossanova. So it's clearly more even, almost completely even, but not quite. It's got this one bigger gap down here. Cool. So that's a unique maximally even rhythm with k equals 5, n equals 16. Another notion of goodness in rhythms is another connection to Erdős here, Erdős deep rhythms. So now we're going to look at a histogram. So let's look at Bossanova here again. Get my shoulder out of the way. So we've got this histogram where we're saying, okay, how many intervals are there of length 1? 0. How many intervals are there of length 3? There's this one, and this one, this one, and this one. So there's 4. So we have a height 4 histogram here. How many intervals of length 4? Just this one. Not just the edges of the polygon, though. We're also interested in the cross diagonals. How many of length 6? There's this one. I think all the dashed ones are length 6. There's 3 of them, and so on. Okay. Now this histogram has this really cool property that there's one value of height 1. There's one value of height 2, one value of height 3, and one value of height 4. So among all the values 1 through k minus 1, there's an interval with exactly that many occurrences. We call this property Erdős deep because Erdős studied this problem in the plane. In 1989, he posed this question: can you place k points, no 3 collinear, no 4 in a circle, to have exactly this kind of distance structure, but now with Euclidean distance instead of intervals? And the largest known such example has size 8. This is a color-coded version where all the red edges have exactly the same length. You can see the coordinates here are quite messy. It's conjectured that they don't exist for sufficiently large k. That's Erdős's conjecture. Probably not even for larger than 8, but who knows? It is known that they exist in higher dimensions, just not in the plane. So we're looking at this, but now in interval distances on the circle. And it turns out among these original 6 patterns, yes, this even one is also deep, but we have this other rhythm called Chico that is also deep. So let me try to play this one. This is a little harder for me. Okay, also sounds cool, right? I mean, all of these sound great. I just have a harder time doing some of them. Now, this rhythm was not even, but you may also notice that all of the onsets are even numbers. So we can divide the whole thing by 2 and get an n equals 8 pattern, which has another name, Cinquillo. and still 5 onsets, but now half as many time units. And in this setting, actually, this is an even pattern. Okay, so maybe deep and even are related, it seems. So what we did in this in a paper of ours is characterize all of these deep rhythms. But these are all examples in the real world of world rhythms that are Erdős deep. There's a lot of them out there. Seems like a cool property. So the idea is your mind can hear these different time intervals. And so if you have this sort of rich mixture of different frequencies of different intervals, then it sounds cool. That's the best I can explain it. Let's get back to mathematics. So it turns out all of the Erdős deep rhythms fall into this very simple structure that they can be generated by a single number that's relatively prime to the number of time units. So here we take the number 7, we start at 0, we add 7, we add 7, we add 7, we add 7. You keep going, and you end up with Bembe, which I will not attempt to play. It has a deep histogram, and in fact, every rhythm along the way is also deep. And every deep Erdős deep rhythm can be generated in this way. You just need to make sure you don't have too many onsets, and you need to be relatively prime. Except for one, there's one exception, which also has a name. It's the Nyanga Mbira. And this one pattern cannot be generated in this way, but it's also Erdős deep. So that's this characterization for this paper we wrote in 2009. So a nice property is that every Erdős deep rhythm can be built up in this way. Usually in geometry we call this shelling, where we're removing items one at a time and preserving the property. So we can start with Bembe. There's an onset we can remove, which is, see, this one, and we still get a deep rhythm. And so you can use this in music, where you build up a richer and richer rhythm as you're adding more and more onsets, but at all times you're remaining deep. So that's a pretty nice property. And we also characterized what the maximally even rhythms are. These are unique, unlike deep rhythms. I mean, here you can see there were lots of deep rhythms, okay, with different numbers of onsets. Okay, but certainly this one is not even. Does not well distribute those 4 points. For example, the only even rhythm with 2 onsets would be this guy and this guy. Okay, so but there's one maximally even rhythm, and it is just integer multiples of n over k with floor. So very simple. You can also think of this as taking a regular k-gon and then rounding each of these vertices to the clockwise next integer. Say. And so you might think there's different ways to do this depending on the initial rotation of the pentagon, but it turns out they all generate the same rhythm up to rotation, integer rotation. But you can also think of this, all of these rhythms are generated by a Euclidean algorithm, the Euclidean algorithm for computing GCDs, which you may have also seen as a line drawing algorithm. So if you've ever coded computer graphics in assembly, you know this very well. When you draw a line from P to Q, and here, notice this is n, and this is k, and you see what are all the pixels that are struck by that line, and you take the upper envelope here, then we have an interval of length 3, an interval of length 3, length 3, length 3, length 4. This is Bossanova, which is even. And in fact, all maximally even rhythms are drawn by this line drawing algorithm, which you can think of as there's these distances of floor of n over k and distances of ceiling of n over k, and you're just trying to maximally evenly disperse them. And as you compute the GCD, you can see where they go. So these are also called Euclidean rhythms. And so it turns out among all these deep rhythms I showed you, most of them are actually even also, except for this exceptional guy, which is not even. And the general result is that essentially all maximally even rhythms are Erdős deep. I won't go through the proof, but you find the generator. It's inverse of 1 modulo n. But of course, not all deep rhythms are maximally even. These are some examples. Cool. So that's our rhythm characterization. I encourage you to check out this book, which talks about these ideas, but many more, including why Godfried loved the Clave Son so much, all the cool properties that it had. That's not exactly deep. It's not exactly maximally even. it's good. And yeah, that's it. I hope you enjoyed this little tour of Godfried's and my work, and I encourage you to continue in the spirit of being super collaborative and sharing and loving and solving open problems. Thanks.